Next speaker is Alexandra Witt, who is a trainee here at UBC under the supervision of Dr. Ed Prysdale. And take it away.
Excellent. Thank you, Ed. Good morning, everybody. My name is Alexandra. I'm going to be speaking to you about my thesis project today, which is working to make a new clot-busting drug using a mutated form of factor 10. So as we all know, heart attacks and strokes are the leading causes of death worldwide, and these are most often caused by blood clots blocking the flow of blood. And this is restored and treated with a recombinant form of tissue plasminogen activator, or TPA here. And this has been fabulous in reducing mortality by over 35%. Unfortunately, there are high doses required, and this causes severe bleeding, including cerebral hemorrhage, in up to 6% of patients. And over the past 3 decades of using this, we have made little to no improvements. So we're working to change that. And we're going to start by talking about the fibrinolytic process here. So this is looking at fibrin, intact fibrin here in red. That forms really the meshwork of the clot. And that'll bring together TPA, in yellow again, with plasminogen in purple. And this will generate plasmin, which is our key clot breakdown machine. Now, with a low amount of plasmin formed, we can get slow fibrinolysis and we'll eventually break this clot down. But what we've discovered in the Prysdale lab is that we can use auxiliary cofactors to influence this. So if we look up at factor 10 in teal, when we start to generate that plasmin and start the clot breakdown process, plasmin will cleave factor 10 into its beta form, which will then act as an accelerant. So that's going to come together and bring together more TPA, more plasminogen, and more rapidly dissolve the clot. With that in mind, we're going to be capitalizing on factor 10 and trying to make a new clot buster. This introduces our double mutant. I'll call it RFXIC. The R is recombinant because we're making this in the lab. And the I and C will be our 2 mutations. So the first on the left, we're looking at the active site of factor 10, or 10A, once it gets activated. And that would form a clot, so we are looking to completely inhibit that by turning that serine, 195 there, into an alanine. So that is our I for inhibitory mutation. And next we have the cleavage profile of factor 10 on the right. So that is factor 10 going down to 10 beta, which I showed before. And then we have a 10 gamma form with another cleavage by plasmin. Now, unfortunately, that gamma form is rapidly cleared by the system, so it's something we're trying to avoid in our drug. So we have a mutation to a glutamine that will allow us to have a cleavage-resistant, or C, mutation. Now, in my studies, I'm going to be talking about a wild-type recombinant form, which will be the basis for our controls. We're going to have a single mutant, which is just that I mutation, another single mutant for the C, and then our double mutant, which is the star of our show. So first up is looking to see if that inhibitory mutation was successful and kind of characterizing how that works. So in a clotting assay where we use factor 10 deficient plasma, we can put in the factor 10 of our choice to watch a clot form. When you add no factor 10 to this preparation, you do not form a clot. But if you add wild-type factor 10, you'll see a clot form in about 12 seconds. Now looking at that single mutant, FXI, we can see no clot formation after our 200-second cutoff, so that is good. That mutation was successful. And if we have a single mutant with just the C cleavage-resistant mutation, we can still form a clot in those 12 seconds, so that hasn't had an impact there. And then, of course, thankfully, our double mutant here does not form a clot in the 200 seconds, so that is another check mark for us. Next, looking at that cleavage profile. Again, we'll start with a wild-type formation. These are Western blots looking at the cleavage of factor 10 over time with plasmin. So we do start with that factor 10 original form, cleave it into a beta form, and then we do get that gamma form in the wild-type. Our single mutant with the inhibitory mutation still has all 3 cleavages, or both of them, sorry, which is, again, successful. We know that that hasn't changed anything there. But when we have the C cleavage-resistant mutation, we're not generating that gamma species. Same again for our double mutant. And this reassures us that our factor 10 is going to have a long-lasting impact on the fibrinolytic efficacies when we put it into our mice. One really important thing for us is that we're trying to make a safer clot buster. And so for here, what we're looking at are anionic phospholipids, which are exposed when a clot occurs. And what we're hypothesizing is that localization to these anionic phospholipids, and perhaps to the fibrin as well, is calcium dependent and the reason that our factor 10 is going to be a safer alternative. And so what we're looking at here, and we'll focus on the left, is a with calcium version of our wild type and our double mutant factor 10s, bound or unbound to anionic phospholipids. And what's most important to take away here is that both in the wild type and double mutant forms, most of our factor 10 is in the bound lane, which means that we are binding in a calcium-dependent manner to these anionic phospholipids. This allows us to move into our preliminary in vitro work, which is looking at, are we going to be accelerating the fibrinolytic process? So again, like I showed before, TPA and plasminogen will slowly generate plasmin. But if we can add our double mutant factor 10, what we're showing here in terms of plasmin generation over time is 10-fold plasmin generation when we're able to add our factor 10. And so this is kind of just the little whisper of what we're going to be doing and what I hope to be finishing in the next few years. So I'd love to talk more about what I'm going to be doing with mice eventually, take some questions now and at the poster session as well. Thank you.
Thank Very nice talk. So I guess maybe I missed it, but so this is all allosteric activation of the activity of plasmin. Is that the way it works? Because the recombinant that you're making has no protease activity itself.
Correct, yeah. So what our hypothesis here is that that little C-terminal lysine that we start to see when we first cleave factor 10 into the beta species, which is by plasmin, is going to help bind the TPA and the plasminogen to that factor 10 localized to the site of the clot. So there's no proteolytic activity. It is all allosteric and kind of bringing everything together to accelerate that process.
So the enzyme which cleaves that factor 10, right? Mm-hmm. Is that, which enzyme? Is that calypsin L?
Plasmin.
Sorry?
Plasmin.
Plasmin. So the secondary cleavage, right?
That is also by plasmin, yeah. So plasmin will continue to cleave it.
Yeah. So would you have, if you somehow inhibit plasmin, would you have the same effect?
Inhibit which, sorry?
No, forget it. I thought it was a different enzyme.
Mm.
Does inactivated factor VIII also inhibit prothrombinase by competitively competing with the wild type factor 10?
It might. We are looking at prothrombinase in terms of an inactivated factor 10, but I haven't used inactivated factor 8 yet, so that might be something that's next up on the docket if you ask Ed later.